We are very lucky today to have Liam Pedersen with us here from the Renault, Nissan, and Mitsubishi Alliance at Silicon Valley, where he is the head of autonomous mobility. Liam got his PhD in robotics at Carnegie Mellon, and prior to working at Nissan, he was at NASA for about 10 years, working on the Mars rover project, where he was part of the efforts to look for life and biological molecules on Mars. And he's going to be talking to us about some of the challenges that they are working on for enabling autonomous driving on our roads. So, Liam?
Okay, thank you. Well, thanks for having me here. It's a lot of fun. I've lived in the Bay Area for a long time, and I've worked a lot with many universities. This is my first visit to Berkeley looking at cars. Actually, last time I was at Berkeley, I was here to work with a professor to look for microbes in the ice. So it's really fun to be back here for this. So I work at Nissan Sunnyvale Center, and what you have over here, these are two of our test vehicles, two of our autonomous cars. Actually been tested at NASA Ames, where we did an experiment for CES in 2006 to operate these cars live from the CES stage and operate them past a bunch of interesting things at NASA. And what this really was about was using NASA technology specifically to deal with the really hard challenges in autonomous driving. And that's what I'd like to talk about today. I'm sure you're all very familiar with some of the normal challenges with driving autonomously, like knowing where you are on a map, detecting things. But I would like to invite you to consider what are the next set of problems. What really makes this hard for introduction to the mass market? And as Jaime said, actually I did used to work at NASA on very slow-moving robots that looked at rocks, and then looked at more rocks and looked for microbes, and never had to worry about dynamic objects around them, at least as far as we know. But now, but fortunately for me, the problems are very similar. You still have to know where you are, you have to deal with uncertainty, and you have to be autonomous. But let me just remind you, first of all, is why do we want autonomous cars in the first place? Why is this such an important problem for our society? Well, the first is quite obvious, is we have 17,000 road deaths every year in the United States. And I just considered that that's about 8 World Trade Center attacks every year. I mean, can you imagine the public outroar that would occur if we had that big of a death toll from terrorist attacks in the United States? And that disproportionately affects young people. But also, more personally, is I have to commute 2 hours every day, and I'd love to have that time back. But, I think there's actually a more important reason to work on autonomous vehicles, and that's just looking at the future of our planet. This is projections of global temperature rises from the past and the future, and if this doesn't scare you, it should. And we're looking at environmental catastrophe. But what has this got to do with autonomous cars? Well, I think we can all admit that transportation is a huge factor in our carbon emissions. And two ways of solving that is to have more people inside every car, so shared transportation, and also electrification of cars. Problem with shared cars is they're really inconvenient. When Zipcar started, you had to walk out to a parking lot, get your shared car, and then you could drive around a bit, and then you had to put it back in the parking lot. Wouldn't it be so much easier if the car that you need just came to you? And that's just it, is driverless cars will really make shared mobility services, and mobility services in general, so much more convenient. And it's those services that can make electric cars economically viable. So, with that in mind, let me tell you about what Nissan is doing. And I'd say we're probably very similar to most other car companies in this regard. But we really see two stages of autonomous car development. There's what we call eyes on and eyes off. So eyes on autonomy is where the driver is still engaged in driving the vehicle, and the autonomy is just helping to alleviate them of some of the workload. But they still have to keep, still have to maybe not have their hands on the steering wheel, but they have to remain engaged in the process. And that will appear first for driving in freeways, so adaptive cruise controls, and it will soon also start appearing for some situations in urban driving and crossing intersections. But what we really want is fully driverless operations. That is where the person inside the vehicle can be completely disengaged, they can take their eyes off, they can do something else. And that is a whole new ball game, because that requires significantly more sensors, and as a result, that will be a significantly more expensive point to achieve, which is why eyes on is likely to be what you'll see in passenger vehicles that get marketed to the public in the near future, and eyes off, the more expensive vehicles, you'll more likely see those in the hands of ride mobility services like Uber and Lyft and other companies, where the passenger does not own the vehicle, but rather is a customer, and as a result, the vehicle is used maybe 80% of the time, as opposed to 4 or 5% of the time, and therefore the cost of the sensors does not become such a big factor. So this is eyes-on driving. This is our CEO, Carlos Ghosn, and driving, this is the Infiniti Q50. At the time, this was the first production steer-by-wire car, and it's leaving our facility here. And what you'll see is that although his hands are not on the wheel, he's still relatively engaged in the driving process. So think of this as more as a partnership or with a car, also an evolution of current safety systems. And note also that the sensors can be kept relatively low profile. So here are the LiDARs, and there's cameras inside. And because he is actually engaged in the driving process, we do not require as expensive and capable sensors as we would otherwise. But, you still need to be careful so far. So, that's great. But what I'm actually really interested in is how can we take that system, or actually how can we take the really capable fully autonomous systems and scale them up for mass deployment. By mass deployment, I mean having hundreds of thousands to millions of vehicles out there on the road. And what does that mean for our society? So, there are still the remaining technical challenges in mapping and localization. Cars right now, they require a very accurate map. They need to know not only the geometry of the road, but they need to know where the lanes are, they need to know where stop signs are, they need to know what traffic light is associated with what lane. And that information is used, not only is it used for planning, but it's also used for interpreting how the other agents are going to move. And we need robust perception. Specifically, we still have the problem with false positives, false negatives, and stopping unnecessarily for other vehicles. But those problems, we've been aware of those for a while. What I'm really interested in is the next problems is of interacting with people How can we make this a socially acceptable car? Because if it isn't socially acceptable, it's actually going to be a business failure. And paradoxically, it's also going to be unsafe. And the reason it's unsafe is if the car doesn't appear, if it doesn't behave like a human car, if it's not socially acceptable, people can't understand what it's going to do. So here we are from a Wired magazine report, recently, just looking at self-driving car accidents, and the vast majority of them are people rear-ending the self-driving car because it stops suddenly, or it otherwise behaves in some unpredictable manner. There have also been incidents where people have been so frustrated by their self-driving car that they do annoying things. Like in this case, a taxi driver that stopped and went outside and banged on the car to indicate their displeasure. Now, imagine scaling this up by 1 million vehicles. Can you imagine the traffic chaos that's going to ensure? And if we don't solve this, we won't have a product. So, yeah, I really love this. Just sort of an example of the fact of how actually, as a robotic system, a self-driving car really has to work within our society. It's not good enough to just avoid hitting this man. We've really got to figure out what that person's intention is. And so we're left with this problem of a robotic system needing to understand what human beings are actually trying to do and then trying to negotiate with them. So here are some subtle examples. Let me just restart that, if I can get my cursor back. So here we have a couple things. So I just want you to first look at the different actors here. Here you have this woman is about to cross over there, and this car is also about to turn. And look at the way they negotiate with each other by pausing very slightly. So there, who's going first? She's going first. No, it's going first. Oh, she pauses, and the car goes round. Meanwhile, look at the other cars. Now, these two cars are in negotiation with each other. Who's going first? They're about the same time, but what you notice is this car is actually about to be blocked by these people over there. And so this driver sees that and also makes the decision to proceed, even though you might argue that the other person has the right of way. And we call that piggybacking. Let me see if I can turn the volume up here. This is video taken by my colleagues in Tehran. Can you hear that? And here I want to point out something really interesting. You see, as she was walking across here, she was looking at the traffic. But at some point she gets to a point she's now assumed priority and she's looking away. And by looking away from traffic, she's communicating that she has priority. If I can see you, that means I'm acknowledging that you can go first. Now, you don't exist anymore. But, I mean, just look at how remarkably efficient this whole process is. Now, see here, he's using his hand. He's just sort of indicating that he's going behind this car. Proceeding. And he's just slowing down very slightly. Now, underpinning, of course, this breaks down a bit, and underpinning this is also the human ability to then renegotiate the passing contract and adjust. So as you watch here, he paused, stopped, and then the problem was very quickly resolved again. So I think there's two lessons you can take from this as a designer of autonomous mobility systems. One is you really do need a model about what other people, what the other actors are trying to do. Not just what they're doing, but what their intention is. And these are rather extreme examples, but you find this very same problem when you're trying to merge into traffic, for example, and you need to understand, is the person next to you going to allow you to get in or not? And if you don't exploit that, there's a gap, they will move in. So that knowledge is important. What's also important is being able to quickly change your decision based on an update on what somebody else will do. And there we are. Okay, so.
Can I ask a question?
Yes, please.
So in the state of California, I always worry at crosswalks. If the person has already walked by and the way is clear, can I proceed and not wait until the person has reached the opposite sidewalk? Just a legality in the state of California.
I really should be able to answer that question. I don't know the legality of that, but I know that many people certainly practice that. And that practice can also vary very much depending on your location. So if you're driving in a location like Berkeley, or where there are lots of students, you actually have to be more cautious because people are jaywalking a lot more because they're running to classes. And the social contract, there's a particular social contract, and then you can go to another neighborhood and the social contract itself changes. So even being aware of the law, what you really want to be able to do is understand the variations and then respond to the variations in each neighborhood. Yes?
The answer is no, you have to wait for the delay in the whole bubble. But I'm not sure it matters outside the driving.
So your question is how do we solve this problem? And we have two ways of doing this. One is to actually be more explicit about communicating our intentions to other vehicles. Now, as human beings, we're very good at doing that just by adjusting the motion of our car, slowing down or speeding up very slightly, and making hand signals. We can't make hand signals in a car, but by at least letting the other people know what we can perceive and what our explicit intentions are, we can actually help reduce the uncertainty over the overall procedure. So, do you want to see that again? So, here we are. So there's two things being shown here. One is communicating the awareness of the other person, but then also saying exactly, it's my turn or it's your turn. Because the goal in the end is not necessarily to cross first or last, but to resolve the ambiguity and make that crossing efficient. But that's not sufficient. What we really want to do is drive as much like a human being as possible. And to do that, we need to take into the fact that we don't fully know the intentions of the other people. and therefore plan with that. And so we have solved that using a POM-DP. And what we're doing over here, this is our test car somewhere else in Sunnyvale. And what you can, let me see if I can pause it. So here we are approaching a stop intersection. So this is the view from our car, and this is what is displayed to the passenger inside. And we're approaching this stop there, and we'll be making a left. And we are already reasoning ahead of time what could possibly occur at this intersection. And now as we come to a stop, what we discover is that there are actually two actors that could conflict with us, and we've instantiated two POM-DPs to account for these two decision problems. So in this case, what we're doing is we're reasoning about our state space in the POM-DP is where we are, where the other actor is, and then the problem with the POM-DP is to choose our action that is most likely to cross that intersection and respond appropriately to the other person. So, based on who has arrived first, we can come up with a priority. And if this starts again, whoops, sorry. And now we have a pause, which I don't want. There we are. So in this case, our belief, timing-wise, is that we arrived first. So we should be number 1, and that's number 2, and that's number 3. And therefore, the correct action is for us to go first. But there's actually a hidden state over here, which is what these two people believe. And this person actually believes that they came first. So as we're about to go, they went ahead. And so our response to that is, instead of just going ahead as well and having a conflict, we changed our action into a state what we call edging, where we just slow down, and instead of trying to cross the intersection, we're just going ahead very slowly to indicate that it's actually our turn. And then we'll go next after them. So then we can proceed. And this behavior is it's useful for claiming an intersection. It's also useful for showing our intentions. But in addition to that, it's something we do when we're getting out of an intersection. We need to look left and right, and we can put the sensors out onto the road and see if the way is clear. So that's great. But now I invite you to consider, what about these situations over here? These are real situations that we've encountered. What will you do as a driver if you encounter this? You're stuck behind here. There's a double yellow line. There's a light over there. There could be high-speed traffic coming towards you. But you can see from the fact that there's road cones and there's people on top here that this is not a person who's stopped. This is an object that's likely to move. But the question arises do you really want your autonomous system to, by itself, decide to break the law and cross this double yellow line? This situation here is also pernicious. Here we have a red light, but this person is waving people on to go. So who do you actually believe? Him or the light? What if this person wasn't wearing a yellow jacket? What if this were a policeman or just somebody standing there waving on the car? And to get here, you've also had to cross a double yellow line, and your whole map is now wrong because that lane is missing, and you have to get through that awkward spot here. And these are hard problems to solve. And the question is, even if you solve one, is your solution to this particular area going to generalize to every other variation that you find? And it is our belief that having an autonomous system deal with every single one of these edge cases is going to take a long time. And if we want to have a service that is out there, we cannot wait until they're actually solved. So what we have done is try to introduce humans in the loop to help deal with these cases, where we have our fleet of cars, and we have a small set of operators whose responsibility is to oversee the cars and just provide them a little bit of assistance. They're not remote drivers, they're more like driving instructors who, whenever a car encounters trouble, can just release some constraints and say, you can go, or you do this. And in this way, we can actually realize a service in advance of waiting the 10 or 20 years that is required to solve all of these edge cases. And that's even been optimistic as to whether those edge cases can all be solved at once. And I think it's worth bearing in mind air traffic control. We've had aircraft now, airline service for almost a century, and it's very, very reliable. There are human beings in the cockpit of aircraft, but also aircraft themselves require an air traffic management system to oversee the entire fleet and to deconflict aircraft as they approach the airspace. But in this case, the important thing is to do this efficiently. Now, and by efficiently, I mean we want to have one teleoperator or one remote person overseeing hundreds or many hundreds of vehicles at any one time. And they can intervene in a number of ways. The most obvious is that they could take control of the vehicle directly, as in remote driving. But that's not a very scalable approach because you need a very high bandwidth, and it takes time to become situationally aware. And there are safety concerns. So what we have been developing is concepts what we call both path-level teleoperation and decision-level teleoperation, where we can either specify a path around some very curious obstruction, where we have a very non-standard maneuver, or even better, just simply tell the car, you can go past this object because it's not going to move, and then let the car itself handle the decision-making of when exactly to stop for someone that walks in front or elsewhere. And I see these modes, they really fall on a whole spectrum of how it is that you want to handle these edge cases. So, with emergency situations, they're very time critical. You obviously cannot handle with teleoperation. The car itself has to be responsible for basic safety at all times. Of course, if the entire car itself fails, well, then you're also out of luck. But if you have a simple obstruction, the onboard system can make the choice to go around by itself. But as it becomes more complicated because of double yellow lines, you now want to invoke the human level support. And this brings up a really interesting research problem, is how can the car by itself figure out when to break the rules, or rather when to call for human assistance? So I'm going to show here is our, this is the teleoperation system built. And what you see here is a car has encountered a problem. It's issued a ticket, which then pops up on this display, this fleet level display. Because it found the problem, it came to a stop. It is now safe. And once the mobility manager has accepted that ticket, They can then see the telemetry from the car and see it's actually a person doing construction, and then zoom into the person over there with sufficient resolution to actually see what any hand gestures are, and then give it authorization to proceed. Now, if you want a robo-taxi service, this is outside your typical airport scene over here. It's quite chaotic. And it's another example requiring a very deep understanding about what other people are about to do. And here is the same system applied to solving that problem here. So here is one of the autonomous vehicles. Now imagine you're responsible for a fleet of 100 or more vehicles. And as it's blue indicating that it does not have any problem. So imagine your person who's responsible maybe doing something else. And this vehicle here is en route to pick up a passenger at this point. And at some point we'll get there. And what the car has decided is that it's actually, from having gone there before, it's too hard a problem. If possible, we will always try to do this autonomously, just for reasons of economy. But it's too hard, so we call for help. And this is then what gets displayed to the remote operator, the mobility manager. You have the raw data from the sensors, as well as images from the front. And what you can see here is there's somebody waving you on. It appears to be an official, an official traffic person. And now we can bring on the human to actually interpret the scene, move on a bit, and notice over here, we can notice that there's a car about to actually pull out over there. Zoom in. Remember, we have to do this over the LTE cellular network, so bandwidth is not guaranteed. So this has to be robust to poor network connectivity. And we see that there's a spot over there, and we can then communicate with the person that we're picking up where we are, and we can adjust our trajectory and then let the vehicle continue by itself autonomously. So the parting message I want to leave you with. So imagine that some fraction of these vehicles here are autonomous, and a couple of them just get stuck in this area and nothing happens. Can you imagine the gridlock and the chaos that's going to ensue if this vehicle is stuck and has no way of dealing with the situation? Even a slow way of getting you out of there is better than no way at all. And the consequence of that is, if we're not able to deal with these situations, is that we will not have autonomous vehicle services inside areas like this, because it'll create too big of a traffic problem, and it would not be used. So, with that, I'm open to questions. By the way, we are hiring, and if anybody is interested in internship, please do call me. We have a really great internship program. You get to drive inside the car. You get to do real work. Your work actually has to be part of the main code base. You get to publish. You get to do patents. And you get paid. Thank you.
Great. So we have a few minutes for questions and discussion. So maybe Eric, do you want to open it up?
I guess related to that last point you made about scaling up autonomous vehicle deployment to some non-trivial proportion of vehicles. If you have multiple companies with their own algorithms and software like deployed, and you have heterogeneous fleets, what do you feel would be necessary for what types of information would be necessary inside protocols if they somehow need to communicate with one another? Say like V2V communication, like what types of information do you feel like would be necessary there?
So before we even get to dealing with exchanging messages between vehicles, which would be helpful, we still have to solve the problem of working with other human beings in the system. And it's not just other drivers, but it's also pedestrians and cyclists. And obviously V2V is not going to help with pedestrians. So there is still that implicit communication that has to occur based on motion. But where V2V could help is in improving efficiency, allowing a vehicle to just slow down very slightly to allow somebody else to pass. And I don't think that's necessarily a V2V problem. I think that's actually a communication of the vehicle state back to the traffic management center, so that you can have a more centralized overview as to what the problem is, because you still got this vehicle penetration problem. And in the case of V2V, I would also be very concerned about the accuracy of information that gets sent from one vehicle to another. And if you only have vehicles communicating point to point, if there is a bad actor in the system, you'll never really know, the other vehicles will never really see that one vehicle for long enough to know. Whereas if you're monitoring it from a traffic management center, you can actually track each vehicle individually and then see anomalous behavior. So I think the long answer is that we really want to network the vehicle. We really like to network all the vehicles and use that data not just for negotiation between vehicles, but actually improving the overall flow of the system. Yeah.
So my car's getting old. It's 18 years old. Maybe it's time for a new car. Should I hang on and wait for this self-driving technology? Or should I just get the best I can and just, it's too far in the future? Which is it?
I think it's going to be a while before you can buy a self-driving car. The sensors are incredibly expensive. They've come down a lot in price, but your Velodyne laser and the GPS, we're talking tens to on the order of $50,000. And if your car is less than $500,000, I don't think you want to add that to it. But where I think that we will see penetration occur quite quickly is in the ride-hailing services and amongst the transportation companies, because in that case, your main cost for a transportation service is the human driver, and that's in the case of Uber, that's 80% of the profit goes to the not the profit, but 80% of the revenue goes to the driver. So they can actually amortize the cost of the sensors much more quickly. And they're also in some cases, facing labor shortages at certain times. So what you'll see is these services starting to appear in specific areas that have been well mapped or well characterized for autonomous vehicles, and then gradually expanding out. So I'd say it really depends where you live. And if you live in the right spot, you'll be able to, you'll have the best of both worlds. You can buy your vehicle and then still get to use an autonomous vehicle as you need.
How many years?
Judging by the amount of money that's been invested, I hesitate to say exactly when, because there are still hard problems. But with the expenditure, I mean, I would say sooner than we think, in the order of 5 years, in limited areas.
Is there a problem with a third party hacking into the system, considering that you can control the cars over LTE network? Is that a real issue? And if so, how do you guys prevent against it?
It will be. Obviously, we'll have to take care of the encrypting the network, and once you open up all the vehicles to remote control, you now have a much larger attack surface. So I think that's one of the very interesting research areas. And the research area that I would be really interested in is not simply defending yourself from hacking, but actually trying to identify problems in the fleet, just from anomalous data in the first place, because you're also going to have things occur because of sensor failures or because the area the car is operating in it's either no longer mapped correctly, or people behaving differently, or you're dealing with greater crowds than you are before. So this general problem of understanding when the system is failing, either due to a hack or through other means, is immensely important for this to be solved. And I think you are best served by looking at data from many cars rather than just a single car, because then you can compare them with each other.
So you showed this slide on Palm DPs earlier.
Yes.
And it seems like that's relying on a robust perception system to actually detect objects. I was just wondering, that kind of got me thinking about, how do you guys think about robustness and failure modes of your software?
Well, one of the advantages of a Palm DP is that you can actually reason about the uncertainty in your detection. And one of the consequences of this reasoning about the uncertainty is we naturally get because it's a partially observable system, right? So we naturally get this behavior that when we cannot see down a road, the lowest cost action is to inch forward very slightly to reduce your uncertainty and therefore make the correct action. Having said that, there's still no substitute for excellent perception. Being able to see people is as far away as you can, and because if your perception is not good enough, your natural instinct is to go too slowly or to be too cautious, and then that brings you into this unsocial behavior that will make the system unusable.
Was it not the case that you instantiate a Palm DP for each car detected? That was kind of what I understood, but maybe not.
Yeah, so that Palm DPs are a very powerful framework, but they don't scale well as you increase the number of actors, and they really scale badly as you increase the dimension, unless you're able to factor the problem. And what we've done is factored the problem into pairwise interactions between different vehicles. So we consider each pair, and then we can take the most pessimistic model from each way, and that way we can scale it up to a large number of actors. And it's proven remarkably effective at dealing with that kind of situation while still remaining very tractable. In fact, it operates in real time.
So, Frank, if you don't mind me cutting in here, because I think it's relevant. I was actually going to ask, so it seems like there are cases where you can get away with this decoupling, right? Especially if you have some sort of situation where maybe you're at an intersection and the problem is naturally decoupleable, in that you can just take the worst case, for example, and say, well, I'm going to wait as long as the worst case tells me that I should wait. But what happens if you have, different kinds of situations where perhaps you have a more naturally coupled system, like you're in, maybe on a highway and there's multiple, you showed this example of the piggybacking at an intersection, but it could also be that a similar interaction happens on the highway between multiple vehicles, where a vehicle is looking at another vehicle that is like maybe going to be in your way before it decides to cut in front of you. How do you think we might be able to deal with those sorts of situations in terms of scaling up and reasoning correctly about our uncertainty?
So I'll give you a partial answer. One of the other aspects of our system is we're able to predict the motion of every single other vehicle. And we do that by using our same path planning framework to predict their motion based on what we can see. So for example, if there's a stopped vehicle in front of us, we have a bicycle next to us, we can use a path planner and figure out the bicycle is going to go around. We see vehicles in front of us, path planner says they need to stop. And we combine that with a hypothesis on what the destination of all the other vehicles are. So they might be going straight, they might be turning left or right. And then we can track all those multiple hypotheses and have a prediction for each possible hypothesis. But in order to make that work, we actually need to have a hierarchy of vehicles. The vehicles in front and not avoiding the vehicles behind.
Right.
So the trick is to create this dependency graph about who is actually interacting with who, and then exploit that structure to make your system more efficient.
Nice. All right.
Hi. So when you were talking about what was it? Hands-on, I think, driverless autonomous vehicles where the human is still paying attention to the road and everything. So I was wondering if the vehicle does get in trouble, by the time the human figures out that it's in trouble, is there still enough remaining time for the human to take control and steer the vehicle out of danger?
I'm so happy you asked that. So the vehicle is always responsible for its basic safety. What we do not want is the vehicle to be driving along at 60 miles an hour, see a problem, and then say, help, I need an operator, help me to stop. That's not scalable. The model is that the vehicle will see a problem, will take whatever emergency corrective action it needs to do, come to a safe stop, and then, and not till it's come to a safe stop can we really expect the human being to take over. Now, we would like the human being to at least become aware of the problem as early as possible, so there's time to become situationally aware, because we don't want the car to be stopped and then just waiting there for a while with people doing that. Now, if we can see the problem from a distance, we'll get maybe 5 seconds or so warning, and that's active research how to solve that. But the other way we solve that is through the network of vehicles, and we log the location of every single known problem and the time, and then that can be communicated. So the next vehicle that's going to go to an area, we'll say, okay, there was a construction at this area, so we can ahead of time choose to either reroute the vehicle or engage a human teleoperator ahead of time, so we can actually minimize that waiting time while we're getting a teleoperator engaged. There's a lot to having the network, the vehicle's network gives you a huge advantage in terms of being able to predict what is going to occur.
Okay, if nobody has another question, I'd like to ask a follow-up to that, which is, so maybe this is a little kind of like thinking down the line, kind of like the corner case of the corner case, but would there be any situations where you might accidentally end up with a vehicle stopping at a state such that the human teleoperator is actually unable to recover, to recover from that stop and put the vehicle back into circulation? So that something happens, on a road where there's some sort of traffic that is time critical enough that the teleoperator cannot just put the vehicle back into the flow of traffic, and therefore the vehicle would end up being stuck, not being able to recover from the failure. Essentially, where neither the human alone or the vehicle alone is able to return to normal driving. What is that something that you should be worried about, or is it a little bit too down the line?
You mean if we created an intractable traffic jam?
Or if you accidentally fell into an absorbing state, so to speak, So the automation finds a situation where it says, oh, I can't go on my own, and it stops. But it stops in such a way that the teleoperator, when they are given control, has to say, well, I don't know how to put you back into traffic.
I haven't
just trying to give you a hard time.
I haven't encountered such a state yet, but I'm sure it could occur. In the very worst state, where you've brought traffic to a halt, you still do have the option of behaving, antisocially, but safely. So you still have the option of just inching forwards, very carefully. At that point, you're going to be disobeying the right of way. You might annoy people. But I haven't encountered a state where you're actually just completely stuck in some place where nothing can be done. It's actually just staying stuck when nothing can be done, especially in a busy intersection, is a really bad option. The very worst thing that can occur is something causes, if you have some complete vehicle failure, so the sensors fail or your autonomy system fails. And in that case, the role of your teleoperator is to call the tow truck.
Right. Makes sense.
Yeah.
Great. All right. One more question. I think we have time.
So that's maybe less of a technical question, but do you have any idea how this would scale with teleoperators? Also, kind of thinking about that in the context of how many jobs would be lost to autonomous driving. I feel like that's something people tend to worry about a lot. Like, do you have any rough estimates of how this would scale?
So let me address the first case and the job losses. It turns out that, I don't know about the taxi companies, but in the trucking business, they're actually anticipating a massive shortfall of truck drivers. So this actually will actually alleviate an impending shortage, for that matter. But what is going to happen to the taxi drivers? I would hope that they'll become teleoperators. In fact, we were contacted by a London cab driver who saw what we were doing on the news, and he said, I want to be a teleoperator. I want to do experiments with this. How's it going to scale? That will depend crucially on the capability of the autonomous system itself, because as the car itself becomes better, becomes more adept at handling situations, it will be requesting assistance in fewer and fewer cases. And we've also designed it so that every time we do have to help a vehicle, we can log that information. And that is actually labeled information that then can be stored and used for machine learning algorithms to grind on and then actually help to improve the system in the future. So it ought to be a system that over time requires fewer and fewer people to operate more vehicles. But how many people you actually need is actually very dependent on the business case, because there are many jobs that this person does besides teleoperating the vehicle. They would also communicate with the car, the passengers of the car. So take, for example, if you have someone with a heavy bag of shopping, and the self-driving car takes them to one side of the road, and they say, no, I want to go over that side. You could try and figure that out with an interface, but it's easier for them to just talk to a person and explain what they want, and then have the car do something. So those kinds of services will also occupy a considerable amount of the teleoperator's time. And depending on that business model will also then affect the number of people you need.
All right, great. I think we're out of time now. So let's thank Liam once again for this great talk and discussion.